For our final mini lecture for this week, we are going to talk about relative velocities. And I will admit, when I learned about relative velocities for the first time in my physics class in college, it was a confusing topic for myself too. So we'll walk through a few examples of these, and you'll see a few more in your homework set for this week. So you will get a lot of good practice dealing with these problems. And relative velocities are all about the perspective of the observer. Relative velocity is all about relating the measurements of two different observers, and those observers may be moving with respect to each other. And anytime we think about velocity, velocity is always relative to some reference frame. A really great example is to think about you in your car. So when you are sitting in the seat in your car, you and the car are moving together. So you do not have a velocity at all with respect to your car, okay? But somebody who's standing on the road watching you in your car drive by, they will see that you have some non-zero velocity. It all has to do with your frame of reference. Where are you standing whenever you're thinking about the motion of the object, okay? What do I mean when I talk about a reference frame? A reference frame is really just a system of coordinates. You can choose a reference frame for you in your car, everything relative to you and your car's motion, or you can choose your reference frame as the stationary observer, everything relative to you standing there as a stationary observer. Typically, we have our stationary frame of reference. That's the observer I was talking about, that's stationary on the ground, not moving, watching something happen, or someone who might be standing on the edge of a river, watching the river flow by them or boats flow by them. Those would be the stationary observers. And then you have your moving frame of reference. So that's a frame of reference relative to whatever else is moving in the system. So maybe that's a boat, maybe that's a person in a car, okay? That would be your moving frame of reference relative to your stationary observer. And again, it's all about your matter of perspective. Depending on which observer you are you stationary or are you moving, you might see the same event happening in a different way. So for example, let's imagine that we have a sailboat here, and that sailboat is moving forward with some non-zero velocity. And you are a person who is standing on this sailboat. Actually, you're at the top of the mast of this sailboat, okay? And you happen to drop a pair of binoculars. And because you are there moving with the boat, what you see in your frame of reference is the binocular dropping straight down. Within your frame of reference, you are moving with the boat, and so everything is relative to the boat's motion. But your friend who is an observer who's standing on the edge of the riverbank watches this same event happen too. And the observer here sees the binocular take a curved path because that boat was moving too. So when you are up here and you're about to drop that pair of binoculars, you have some forward velocity because you're on the boat. And that means that those binoculars have some forward velocity too. That forward velocity is with respect to this person here who's stationary on the ground. And so because this binocular has some forward velocity, you let it go, it's going to travel the path of a projectile. Okay, so let's say that the forward velocity is 5 meters per second. Then the horizontal velocity of this binocular is also 5 meters per second forward. And so it's moving forward at the same speed as your boat is moving forward, okay? And so relative to you, you just see that it drops straight down. But someone down here will see that pair of binoculars executing a projectile motion path. Okay, so it's kind of a weird thing to wrap your head around, but the motion of an event can look different depending on your reference frame. So how do we perform our relative velocity calculations? Well, let's walk through it here. There'll be an equation that we can use. So in this example here, let E be an observer, assumed stationary with respect to the Earth. So E, our observer, is going to be standing right here. We'll say that they are at the center of their coordinate system. So E is going to be right here, okay? And then let's have two cars that we label car A and car B. So here's car A, here's car B, okay? And we call this vector R sub AE, the position of car A as measured by E, who is stationary, okay? E is in a coordinate system fixed with respect to the Earth. So E stands here and measures this position of the car to be over here. So that's the position of car A with respect to our observer, okay? And then here we have this vector, R sub BE, which represents the position of our car, B, as measured by our stationary observer at E. So then we want to know, what is the position of car A as measured by an observer in car B? Okay, so these two observers are going to be moving with respect to each other. Okay, we could also solve this problem to find the position of car B as measured by an observer in car A. We could do that too. But let's just focus here on finding the position of car A as measured by an observer in car B. Okay, and so this equation right here is how we would do it. There's a method we can use. So the position of car A relative to car B is equal to the position of car A relative to our stationary observer minus the position of car B relative to our stationary observer. And so the order in which you subtract them, if we were looking for the position of car A relative to car B, then we have to put first in this equation on the right-hand side of the equal sign, the position of car A, that's that first subscript here with respect to the stationary observer, minus, now we've got our second subscript, the position of car B with respect to our stationary observer, okay? And then if we wanted to find the velocity of car A with respect to car B, similar idea. We have to take the velocity of car A with respect to our stationary observer minus the velocity of car B with respect to our stationary observer. Now, if instead I wanted to find the velocity of car B with respect to car A, then we would swap the order of these velocities that you see in this equation right here. So this first subscript A representing our mover car A, we have to have the velocity of car A with respect to the Earth here first. And for a second subscript here on the velocity, we have to, that's the velocity we're subtracting off. And so then the second term here in this equation would be the velocity of our second object with respect to our stationary observer. So we take this equation, and depending on what I'm asking you to solve for, you can rearrange this equation to solve for any one of those three terms. So the first letter tells us what the vector is pointing toward, and the second letter tells us where the vector starts, and that's why we've got the A first and then the E second. So if we look up here at our vector for the position of car A with respect to the Earth, the first letter tells us what the vector is pointing toward car A, and it originated back here at our stationary observer. So we're going to use our relative velocity equation right here in order to solve a problem, something that you might have even experienced a similar thing in your real life, okay? So we have a boat that is heading due north as it crosses a river with a velocity of 10 kilometers per hour relative to the water, to the flow of water, okay? The river has a uniform velocity, a flow of fluid of 5 kilometers per hour due east. So our river is running to the east. Our boat, with respect to the river flow, is going due north, so they're perpendicular to each other at 90 degrees with respect to each other. So we're going to determine the velocity of the boat with respect to an observer on the riverbank. So for a person sitting in the boat, they'll feel like they're just moving toward directly the opposite shore. But then the person who's standing here is going to see this vector of motion right here, is going to see that boat appear to drift toward the east because of the flow of the river. And so we're going to work through, using our relative velocity equations, how to figure out the velocity of this boat with respect to a spectator who might be standing here on the riverbank. So our problem is we have a boat that is going to be heading due north as it crosses a river. Here's our river. And the boat, as it heads due north, is crossing our river with a velocity of 10 kilometers per hour relative to the flow of water, or sometimes I'll say relative to as with respect to the water, okay? And then we also know that our river has a uniform flow of 5 kilometers per hour to the east, relative to an observer standing here on the bank of the river. And so our question is, what is the velocity of our boat with respect to an observer on the riverbank? Okay, so what's happening is that our boat is trying to go north, okay, but the river is flowing this way to the east. And so from somebody who's standing here on the edge of the river, from their perspective, it's going to look like that boat is going to be drifting off in this direction. But if you're a person in that boat, you're just going to experience you moving straight toward the bank of that river on the other side. Okay, that's all about our relative velocities. The motion looks a little bit different for the stationary observer right here than the person who's actually in that boat that's moving across the river. Okay, so what we have to do is figure out the velocity of our boat relative to our observer on the riverbank here. Okay, to solve this problem, we are going to use the equation that we just talked about for relative velocity. So from there, we had our velocity A, B, the velocity of object A with respect to object B, equals the velocity of A with respect to the Earth, or our stationary observer on the Earth, minus the velocity of object B with respect to our stationary observer on the Earth. Okay, so we are going to do a similar format here in order to solve this problem. Okay, so what we need to find is, so this was the example. Okay, what we need to do is right here. We want the velocity of our boat, we'll call this B for boat, the velocity of our boat with respect to the observer on the riverbank. And so if the observer is stationary here, we're going to represent that as E right here because that person is stationary on the Earth. So we're looking to solve VBE in this case, the velocity of our boat with respect to the observer on the riverbank. Okay, and so if we're going to model our equation for relative velocity from this example right here, then the little subscripts that we have to keep in mind are Earth, that's our observer. And here I'm going to use B for boat. And here I'm also going to use R to represent everything with respect to the river flow. Okay, so we're going to have the velocity of our two objects that are moving. So the velocity of our boat with respect to the river is equal to the velocity of our boat with respect to the stationary observer here minus the velocity of our river with respect to our stationary observer here. Okay, the thing that we want to solve for is the velocity of our boat with respect to the observer. So I'm going to solve this equation by bringing V sub RE to the other side. So this becomes a vector addition problem. So then the velocity of our boat with respect to the stationary observer equals the velocity of our boat with respect to the river plus the velocity of our river with respect to the stationary observer here. Okay, so we're looking for this vector right here. We actually know vector B sub R, or we actually know this vector here, sub BR, and we know this vector here, sub RE, river with respect to the Earth. So let's draw in these vectors over here. Okay, so we've got our boat going due north, okay,
And this is the velocity of our boat with respect to the water, or with respect to the river. So we've got V sub BR equals 10 kilometers per hour, okay? And then we're going to be adding it on to the velocity of our river, or our water, with respect to our stationary observer. And that's the fact here that our river has this uniform flow of 5 kilometers per hour to the east. So I'm going to add that vector on right here. So this is vector R sub RE, the velocity of our river with respect to our stationary observer here, okay? And that we know to be 5 kilometers per hour. So the sum of V sub BR, boat with respect to river, plus the sum of the velocity of our river with respect to the Earth is going to give us our resultant vector here. That's this vector. That's representing our vector sub BE, the velocity of our boat with respect to the Earth down here. Okay, so what happens is that the person that's in the boat is going to feel like they're moving straight toward the riverbank, okay? But the person here on the Earth is going to see the motion of the boat look like this. It's going to see the motion of the boat kind of drift off into the east here. And so we're going to figure out the magnitude of this vector here and its angle with respect to due north here, okay? So this becomes now just a vector addition problem after we talked about this. Okay, so let's think about our vector sub BR, okay? This vector here only has a component in the y direction, okay? So it is just going to be 10 kilometers per hour in the y hat direction towards the north, okay? And then vector RE only has a component in the x direction, and that's going to be 5 kilometers per hour x hat. And because it's to the east, that's along the x direction. Okay, and so we have to add these vectors. Essentially, vector BR has no x component. Vector RE has no y component. Okay, so the sum of these vectors is going to look like the x component of BRX plus the x component of VRE, x hat, plus the y component of VBR plus the y component of VRE, okay? And so if we're looking at V sub BR, it doesn't have an x component. If we're looking at velocity sub RE here, it doesn't have a y component, okay? And so then our vector BE becomes just the component of this vector here in the x direction, so 5 kilometers per hour x hat, plus the y component of vector sub BR here, and that's 10 kilometers per hour y hat, okay? So that's what this vector, the velocity of our boat with respect to the Earth, looks like in unit vector notation. So it's going off to this direction, so we have to go to the right 5 along the x-axis and up 10 along the y-axis in order to get this vector here, okay? And then we want to find the magnitude of this. And so that's essentially us applying, again, the Pythagorean theorem. So the magnitude of, oh, don't want to put it on there. The magnitude of vector for our velocity sub BE equals the square root of our x component here, which would be 5 squared, plus the y component here, 10 squared, okay? And so then that equals 11.2, and I dropped the units out of here, kilometers per hour, okay? So that is the magnitude of this velocity here, vector sub BE, which is the velocity of our boat with respect to our stationary observer. And so we had to use relative velocities in order to solve for that. And then we also had to use our vector notation and apply Pythagorean theorem in order to find the magnitude of that vector here, which we find to be 11.2 kilometers per hour. And then because velocity is a vector, we've got our magnitude, but we need to find the direction. We need to find the angle of this vector with respect to, let's just say with respect to due north right here, okay? And in order to do that, you can use tangent of theta. So if this is our angle theta right here, then we can say that tangent of theta is equal to opposite, so that would be our 5 kilometers per hour, over adjacent, which would be our 10 kilometers per hour. So theta is going to equal, these units cancel, the inverse tangent of 5 over 10, and then that turns out to be 26.6 degrees, okay? So the velocity of our boat with respect to our observer on the riverbank then is 11.2 kilometers at an angle of 26.6 degrees from due north.